All right, in this video we're going to talk a little bit about water and its general properties. And this will be a focal point because we're going to carry through in the rest of this chapter to talk about aqueous reactions, aqueous solutions. Again, if you're following along in your book, this would be chapter 4, section 1. All right, so what's so important about water? Well, I think you know the answer to that. When we talk about aqueous chemistry, we mean chemistry that occurs because of the unique properties of water. Okay? I used to have a long list of other things about why water was so important. There's no time for that. I'll just say, consider it's a universal solvent and it's liquid over a wide temperature range. That's what allowed it to be a solvent that is used for a lot of the naturally occurring chemistry, whether on the biological side or the non-biological side. Okay, list a few more things about water. This slide in here is just some interesting asides about water. You've probably heard in your biology class that water is called liquid life, and again, it's because the reactions that occur in our bodies in any living organism occur in water. Okay, and you probably also heard this in your biology class, right? Approximately 60–70% of the human body is water. 70% of the Earth's surface is water. Okay, I got this little graph here to show this. This was a surprise to me. I knew that 70% of the Earth's surface was water, and most of that is in the ocean. But of the fresh water, most of that actually is bound up as groundwater or as ice in the glaciers. There's only a very small percentage that exists in what we know as the rivers and lakes and swamps. Okay. Okay, so let me introduce you to a couple of new terms, and we'll start off by reminding you what we mean by a solution. A solution is a homogeneous mixture, right? That means two or more substances combined together, and when you're done, it looks like one homogeneous substance. The perfect example is sugar or sodium chloride stirred in water. What you end up with looks like clear liquid, but in fact it has the sugar dissolved. In fact, you could put in sugar and sodium chloride and a bunch of other things, let it dissolve. That's a mixture of two or more substances in a homogeneous. What are the components of a solution? Well, let me go back. I forgot to mention this asterisk. Remember that technically we can call solids as solutions if they are mixtures of metals. So bronze is primarily copper, and it's got some tin in there, I believe some nickel and so forth. But when it's all melted together, it looks like one type of metal. That's a solution, a homogeneous mixture. Okay, so what are the terms I want to introduce? Solvent. Solvent is the substance in the greatest amount. So in this case, our solvent would be water. And since we're talking about aqueous solutions, more times than not, our solvent is water. Now, when you get to organic chemistry, you're going to be talking about solvents that are organic compounds, and you'll learn about how that affects the chemistry that you're looking at. The second component of a solution is the solute. Solute is the substance that's in lower amounts that is dissolved in the solvent. Okay. Now, what do we say dissolve? Because in reality, you can have a solution that's made up of, say, water plus ethanol. Ethanol is a clear liquid, so it doesn't have to be a solid to be a solute, but most of the time we associate a solute as something that's solid that then dissolves in water. Okay. This next section, a little subsection, is to talk about what we call electrolyte properties. And so my first question to you is, what are electrolytes? Okay, well, I'm going to introduce you to this by a little video that I like to show from a movie.
For the last time, I'm pretty sure what's killing the crops is this Brondo stuff.
The Brondo's got what plants crave. It's got electrolytes.
So wait a minute. What you're saying is that you want us to put water on the crops?
Yes.
Water? Like out the toilet?
Well, I mean, it doesn't have to be out of the toilet, but yeah, that's the idea.
But Brondo's got what plants crave.
It's got electrolytes.
Okay, look. The plants aren't growing, So I'm pretty sure that the Brondo's not working. Now, I'm no botanist, but I do know that if you put water on plants, they grow.
Well, I've never seen no plants grow out of no toilet.
Hey, that's good. You sure you ain't the smartest guy in the world?
Yeah.
So let's go back.
Okay, look, you want to solve this problem. I want to get my pardon, so why don't we just try it, okay? And not worry about what plants crave.
Brondo's got what plants crave.
Yeah, it's got electrolytes.
What are electrolytes? Do you even know?
It's what they used to make Brondo.
Yeah, but why did they use them to make Brondo?
Because Brondo's got electrolytes.
All right, that's a great movie. For those of you who haven't seen it, it's called Idiocracy. Some people would argue that the movie is actually depicting the sort of state of affairs that we're in right now. So most people, when they mention electrolytes, they talk about coconut water. It's got electrolytes. Gatorade's got electrolytes. A non-science major will never know what that is. Okay, what are electrolytes? Electrolytes are simply substances that dissolve in water to form ions. Ions being a positive entity is a cation and a negative entity is an anion. Once those are in aqueous solution, it allows the solution to conduct electricity. Okay, here's an example. Sodium chloride. Sodium chloride, solid, dissolved in water. Remember, we write this AQ to indicate that a substance is dissolved in aqueous solution. So we write the sodium cation with a plus charge, a chloride anion with a negative charge. By the way, you ought to know whether it's written this way or simply sodium chloride AQ. This way indicates this, so you ought to know the interchange between. But really, the sodium cations and the chloride anions exist separately in the water floating around. This allows electricity to be conducted. Non-electrolytes are simply substances that, when dissolved in water, do not generate ions. So an example of that would be ethanol. Okay, this is ethanol with water, and we still put the AQ next to ethanol, which denotes that the molecule is in the water as a solvent. Okay, but you notice there's no plus or minus here, so there's no conduction of electricity. Okay. You may have seen this demo in your high school chemistry. You can demonstrate an electrolyte by putting it into distilled water and then trying to apply electric current across this. If it's an electrolyte, the bulb will light up. If it's not, the bulb will not light up. Okay, so again, ions allowing the resulting solutions to conduct electricity. It's very important too. The number of ions in solution is proportional to the amount of electricity that can be conducted. So what does that mean? That means if I put 1 gram of sodium chloride in 1 liter, that's not going to be as conductive as 10 grams of sodium chloride in 1 liter. So that's all this statement means. Okay. So getting back to electrolytes and Brondo or Gatorade, most students are interested in this after hearing what the definition of electrolytes are. What are the electrolytes primarily in a substance like Gatorade? Sodium chloride. Remember, when you see that, think of it as the sodium and the chloride anion, sodium citrate, which is the sodium cation and the citrate anion. Don't worry about that complex formula. And potassium phosphate, what plants crave. By the way, the main electrolytes in blood are sodium, potassium chloride, bicarbonate, calcium, and magnesium. So when we're trying to replace electrolytes with a substance like Gatorade, we're angling towards mainly these substances. All right. So I think you can see from the previous slides that it's important when you write these chemical reactions down that you be able to identify the cation and anion species present in the electrolyte solution. So in other words, if I wrote down potassium chloride solid and gave you the arrow, you ought to be able to write down the potassium cation and the chloride anion with the AQ to denote that it's in solution. Magnesium nitrate, solid. Okay? When that dissolves, you get 1 magnesium cation with a +2 charge. Okay? And 2, that 2 comes from the subscript there, 2 nitrate polyatomic ions. Okay. How about these last 2 that I wrote down? Let's go through this. So we've got the cation's ammonium, the anion's phosphate. You would have 3 ammonium cations, AQ, plus 1 phosphate anion AQ. HCl, turns out pure hydrochloric acid is a gas, but when you put it in water, it immediately falls apart, and you get H plus AQ plus chloride AQ. We will talk about acids and bases in another lecture. Okay. So let's talk about a little bit more about why ionic compounds dissolve in water, okay, and what happens with the water molecule. Now down this lower portion of the slide is a depiction space-filling model. Remember we talked about that in a previous lecture of water. So we've got the oxygen and the two hydrogens. And notice the minuses and plus here. What does that mean? That means the water molecule is what we call polar. That means that, remember, an electron has a negative charge, protons have a positive charge. So in this distribution of electrons around the atoms in the molecule, if you've got one side of the molecule that has sort of a more electron-rich versus another, it generates this, what we call a polar nature. And we'll get into this more when we talk about covalent bonds. Okay. So when an ionic substance dissolves in water, the solvent, water, pulls you can envision pulling the actual ions apart, and we call that solvation, also sometimes called dissociation. Now, most books have a picture similar to the one I'm going to show you. It's this. So picture a sort of crystal of sodium chloride is this three-dimensional lattice, right, where the purple spheres are the sodium cations, okay, that would be this, and the green spheres are the chloride anions. So what this picture is trying to show is the water molecules come along, basically pick off these ions from the big mess. Okay, now it's important to look closely at this picture. Notice that the orientation of the water molecules. So if you look at this set right here, you'll notice the cation, the sodium cation, has the water molecules oriented, okay, with the oxygen atom towards it. Okay. And the reason is because positive attracts negative, negative attracts positive, and the negative portion of the water molecule is going to be oriented to the positive cation, sodium cation. Okay. Likewise, if you look here, we've got the chloride anion, shown as a little bit bigger, and in this case, the hydrogens are going to be oriented towards the chloride ion. Again, because you've got the positive side of the polar water molecule. So it's this polar nature of water that allows it to pull these ions apart. Okay. All right. What about molecular compounds of water? Okay, can see that an ionic substance dissolves because of this polar nature of water, and you've got your pluses and minuses floating around, and those are sort of shielded. It's called the hydration shell by the polar water molecule. What about molecular compounds that are not electrolytes, non-electrolytes, and therefore don't have positive, negative charge? How are those things dissolving in water? Okay, well, this next subsection, we're going to talk about molecular compounds in water. So we saw that ions will dissolve in water because of the polar nature of the water molecule, right? It's typically drawn like this. A Greek symbol indicates partial, so partial positive, partial negative. There's your polar water molecule. But molecular compounds we mentioned there are non-electrolytes. So what is it about water that allows molecular compounds to dissolve? Okay. Since they are non-electrolytes, they don't form ions. Okay. We're talking about acids and bases. It turns out that acids are molecular compounds that form ions, but we'll come back to that. So here's a nice little picture showing methanol. Methanol is essentially what looks like a methane molecule with an oxygen attached to it. Okay. It's still the polar nature of water that allows this substance to dissolve. Why is that? Because methanol itself is polar. Okay. So if you look at this methanol molecule, we look at the oxygen as having the partial negative charge on it, and the carbon entity is partial positive. So this association of the plus minus, minus plus between the methanol and the water, similar to cations and anions, is similar to what allows the polar water molecule to dissolve molecular compounds. Okay. Let's get back to electrolytes and further define what we mean in terms of strength. Okay, so strong and weak electrolytes. A strong electrolyte dissociates completely in water. Right? And a good example of that is sodium chloride. So sodium chloride, solid, water, basically 100%, as long as you don't overload it, and you're going to have the sodium cation and the chloride anion, right? Okay. A weak electrolyte only partially dissolves. And we're going to learn that ionic compounds aren't always freely soluble. That's coming up in a subsequent video. Okay, so if you put a substance, I'll just write this X, Y, into water, it may not completely dissolve. And then what we can write is this double-headed arrow, meaning that of the total amount of substance, some of it dissolves and you've got the ions, and some of it stays as a solid. So you can kind of picture a beaker with water in it. We put our substance in, dissolve it, stir it. We've got the X, Y solid down at the bottom, and then up in here are the X and Y. And since we said that the amount of conduction electricity is proportional to the number of ions, the substance that only partially dissolves is considered a weak electrolyte. Okay. Here's a table. This is actually not in the 13th edition, that tries to put some definition, classification to strong, weak, ionic, molecular. So we've got listed here all ionic compounds as a strong electrolyte, where it turns out that that's not true. We'll come back to that. The strong acids for molecular are electrolytes. Weak acids, weak bases are weak electrolytes, and all other molecular compounds are considered non-electrolytes. Now, don't be confused by this now. You'll get a feel for this later. So let's come back to this part about ionic compounds. Why is it that not all ionic compounds are strong electrolytes? This table says all. Well, it's the reason I just said. A perfect example of that is silver chloride. Okay. Silver chloride is a prototypic ionic solid. We've got the silver cation combined with the chloride anion. You would think if you put that in water, you're going to get complete dissociation, and you've got this. Well, in reality, we have what's called partially or insoluble ionic compounds. Okay, and that means that certain ionic compounds don't fall into this category of strong electrolytes. They are actually weak electrolytes. So this is a fine point, but it's also very important. Okay, so that's this last statement. Many ionic compounds are insoluble or partially soluble, meaning only a small percentage it dissolves and creates ions. Okay.